All right, so last time we defined kinetic energy for rotations. Okay, we call it rotational kinetic energy, and the equation we use is this: 1/2 I omega squared, and then it's equivalent to the equation we used for the kinetic energy in linear motion, right, or translational motion. And then if you take a look at the table on slide 1, lecture 16, okay, now you see the connection between all these things we have defined, right? And then even the connection between them, okay, you see that all you need to do is just replace mass with its equivalent I in rotations, replace the velocity with the equivalent angular velocity in the rotation. So everything's consistent. It's a complete and consistent theory. So of course, once we have defined this kinetic energy for a rotating object, we can still use conservation of energy in rotations, right? And then gravitational potential doesn't change. It's still mgh. But now this height is a little bit tricky. So the height is where the center of mass is, right? Because in this case, when something's rotating, every point can be at a different height. So the height we plug in this mgh is going to be the height for the center of mass, okay? And then, that for a rolling object, you only need this term, okay? So that's the problem we did last time. When something's rotating, for a rotating object, you only need this term for a rotating object. Something's rotating about a fixed point, okay? And then when something's rotating, when something's rolling, okay? Rolling motion is a combination, right? This is rolling, this is rolling, this is rolling, right? It's a combination of rotation and a straight line motion, okay, of the center of mass. So in this case, it's going to have these two versions of kinetic energy. So all you need to do when you apply conservation of energy, you're going to have this term and also that term we have been using in linear motion. So as I said last time, actually a lot of people, they will forget this term because they remember, oh, we learned a new term for the kinetic energy, 1/2 I omega squared. I'm going to keep that in mind. But when something's rolling, it's also moving in straight line. So it still has this 1/2 mv squared. So don't forget that term. And then you will still do gravitational potential energy, elastic potential energy equals external work. Okay? So that's the only difference between a rotating object and a rolling object. Now we're gonna, and of course, you can always connect, when something's rolling, you can always connect the distance and the angle it rotates, the velocity, linear velocity, and the angular velocity, the linear acceleration and the angular acceleration, right? So we know they're all connected by the radius of this rolling object if it's a circle. And then these equations are in slide 4, okay? Now let's take a look at a problem. We're going to practice this theory again. So this is actually an experiment I showed you the first day of the semester, if you still remember that. I used this question to show you that a lot of questions in physics are not intuitive. You can't figure it out using your own judgment, using your own experience, right? So this is one of the experiments, and we're going to do the experiment. The experiment is this. I already have them set up here. Make sure you can see that. Okay, so what we have here is that there's a ramp, but then if you have a disc and a hoop, okay, they have the same mass and the same radius, right? If I let them roll down the ramp from the same height, and then of course gravity is going to pull them down, right? So they're going to roll down the ramp. But my question is this: which one is going to reach the bottom of the ramp the first? Okay, again, this is not intuitive at all. Okay, you can guess the answer, okay, but there's no way you can explain that. Now, what we're going to do today is to use this new theory, new term we learned, and then still apply conservation of energy to answer this question. So how do I decide which one is going to win the race? How do I decide which one is going to reach the bottom first? Well, if I can predict their speed at the end, so which one is going to have the largest speed is going to reach the end faster, right? So that means that object is always going to be faster than the other if it has a faster velocity at the end. So that's what I'm going to do. I'm going to derive an expression for the velocity of this object at the end of the ramp, and then I'm going to compare the velocity for these two guys. Okay, which one has a larger velocity at the end? And that guy is going to be the first one to reach the end of the ramp. Okay, so this is our question. Slide 6. Okay, so now we're going to use all symbols because at the end I'm going to use the same conclusion. I want to draw an expression. So I'm just going to use the expression and then plug different numbers in for these two guys. I'm going to see the difference between them and then use that expression to determine which one is going to have a larger speed at the end. Okay. So I'm going to use all symbols. A rolling object, okay, a mass m and radius r, so they have the same mass and radius, okay. And then if the height, and actually at the end you can see that the mass and the radius doesn't even matter. If the height of the ramp is h, okay, all symbols, and the moment of inertia of this object is I. So let's just use this I. And then if we want to compare, we're gonna look it up in the list, okay. We want to find the linear speed of object at the bottom of the ramp, okay. Now I'm going to set up conservation of energy. Why do I pick this law? You see that something's rolling down, so there are different heights here. So for different heights, I would prefer to use conservation of energy. And then conservation of energy does have speed, linear speed and angular speed in this equation. So I can use them, conservation of energy, to find this speed. Okay? Now let's see, let's set it up. So setting up these conservation laws is very easy. I don't even need the detail of the problem, right? This guy, it's always going to be 1/2 I final squared minus 1/2 I initial squared, right? Okay, the linear kinetic energy is the same, final minus initial. Okay, and there is a gravitational potential energy because it's rolling down the ramp, the height changes. So I will have mg h final minus mg hi. Now, I don't have any elastic system here, so there's no elastic potential energy. And then again, the work from outside is 0 because the gravity is down, right? And then the normal force doesn't do work. We have done that many times, okay? Gravity doesn't go to the right-hand side, okay? Normal force is not doing work. Now I'm going to rearrange this equation, okay, to find remember what we want to find. We want to find linear speed of the object at the bottom of the ramp, which is this VF, okay, which is this VF. Now let's see. A lot of symbols, but let's see if we have any zeros, right? This guy is 0, initial 0, right? Because they are released. So at the very beginning, they're not moving, they're not rotating. This is 0. And these two heights, I can call the final height 0, because that's already the end of the ramp. And this hi is just going to be the h in the problem. Now let's get rid of these zeros. So I'm only going to have 3 terms here, 1/2 I omega final squared plus 1/2 m vf squared minus mgh. The initial height is just the height of the ramp. Now you can rearrange this equation to find an expression for the VF. Okay, but wait a moment. I, M, H, they are variables. They are variables from the problem. I can just use these symbols. What about this omega f, right? I want to find a VF, but that's another unknown. But again, remember, linear quantities and angular quantities, they're always connected by R, okay? So that means they're always connected. So VF is going to be equal to R omega F. So which one do I want to find? I want to find VF. So let's just get rid of omega F. So I don't need the omega F in the problem. So the angular speed at the end is going to be this divided by mu1. Okay? Then you see that this is going to become one equation with one unknown. VF R squared plus 1/2 VF squared. And then move this term to right, mgh. Now solve this equation, get expression for VF. Work with the symbols, okay? Treat the symbols as numbers. The only variable, the only x is this VF. How do you get this VF, right? So do the algebra, see if you can get the right answer. All right, so let me do it. So first of all, I want to, so this is going to become, let's square that out, 1/2 I VF squared over R squared, right, plus 1/2 M VF squared equals mgh. Now this is x, this is x, x times a number, okay? Don't be afraid of the symbols. X times a number, x times a number. You can factor out x, right? You can factor out x. So what do we get? If you factor it out, you would get VF squared 1/2 I over RF squared, right? Plus M, 1/2. Equals mgh, right? And then just divide both sides by this factor, you will get a VF, and then take a square root, right? So, okay, VF squared is gonna be mgh over 1/2 I over RF squared plus 1/2 M. Okay, then square root. Okay, now you see, if I have all the numbers in, I can just plug them in, right? You have all the numbers. But now I just want to find an expression. Which one is going to be this expression? Well, this doesn't look like any of the answers, so that means I can simplify it a little bit, okay? I can simplify it a little bit. So I'm going to do it here. So first of all, I multiply the numerator and the denominator with 2. I can get rid of this 1/2 at the bottom, right? So if I multiply the numerator with 2, I get this. Multiply the denominator with 2, I get I over RF. No, there's no RF. What am I? No. Okay. The radius doesn't change. There's no RF. I'm sorry. Okay. R squared plus M square root. Right. Well, it still doesn't look like any of these answers, because at the top, for each answer at the top, that's 2gh. Oh, that means if I divide the numerator and the denominator with mass, right? Divide this with mass. Divide this whole thing with mass. What do you get? The top is going to become 2gh. The bottom is going to become I over mr squared plus 1. Right? Okay, so that's gonna be E. That's gonna be E. Okay, so now why do we want to get this expression? So this is the simplest you can get. Now I'm going to erase all this. Okay. And then now you see that this is going to be the expression for any object rolling down the ramp, right? So GH is going to be the same, okay, if some object is rolling down. So the only difference is in this term, right? This thing is going to determine how, which one is going to be faster, which one is going to be slower, right? Everything is going to be the same for any object rolling down. So now we can see that I need the I. Okay, for different object, it has different I. So let's take a look at the list. So I attach the list again on slide 7. For the hoop, what is the I? So that's gonna be the first one, right? M times R squared. So that's just gonna be M times R squared. For this disk, I should use the third one, right? The solid cylinder, that's gonna be, or disk, okay? So for the disk, the I is gonna be 1/2 mR squared. Now let's see. If you plug this I in, what do you get? So the VF for the hoop is gonna be 2GH. Now you're gonna get I divided by mR squared. Oh, that's gonna be 1. So it's 1 plus 1. That's gonna be 2. Now this, for the disk, you will get this. 2GH. You still have I divided by mR squared. That's why I want to put them in there together. 1/2 plus 1. Which number is going to be larger? Okay? So this number is smaller than that, but this is in the denominator. Okay? So that means this number is going to actually, this whole number is going to be larger than that. So the disk, it's going to be faster than the hoop. That's our conclusion, right? Because at the end, the hoop is going to reach a larger speed. Of course, it's going to be faster. Okay? So you see that at the end, it doesn't really matter. The m and r squared, you don't even need that. So they don't even need to have the same mass or radius. Okay? As long as they are rolling down the ramp, then the conclusion is always true. Now let's do this experiment. Our conclusion is that the disk is going to win. Okay, so let's do that. I'm going to place them at the top of the ramp, let them roll. The disk always wins, right? Doesn't matter how you do that. Right? So it doesn't matter at which height, right? Let's do it here. Disk still wins. Disk still wins. Okay? All right? So this is another example where when things are not intuitive, okay, you can't figure it out using your experience. Actually, we only have a very limited experience, okay, with things around us. You use math, you use a physics theory, right? You do the math. Math is more reliable than our intuition, than our experience, okay? And this is also a practice on conservation of energy for a rolling object. And then again, for a rolling object, remember, you always need to include both this and the usual kinetic energy 1/2 mv squared. All right? So this is this question. Now, let's take a look at the next question, slide 8. Okay? So let's just do one more practice. A ball rolls without slipping along the track shown below. It starts at the rest, from rest at this height, h equals 3.5 big R. Big R is the radius of the loop at the bottom. Right? Find the linear speed of the ball when it reaches the point P. Okay, I see rolling object, right? And then I see different heights. Okay, I'm going to use conservation of energy again, right? Because it's going to have two different versions of kinetic energy. It's going to also have mgh. So I will still use conservation of energy. Now let's set up conservation of energy. And when you set up conservation, it's the same way, right? You always set it as the same way. Changing rotational kinetic energy, changing translational kinetic energy, changing gravitational potential energy, and there's no elastic potential energy here. Equals external work. Okay? Now, you see that you will set up exactly the same way like what we just did. 1/2 I omega final squared, 1/2 I omega initial squared. Right, and then plus 1/2 mv final squared minus 1/2 mv initial squared, mgh final minus mgh initial, and then still gravity doesn't go to the right hand side, normal force doesn't do work, you got a 0 on the right. Now let's put all the symbols in. We don't have all the numbers. We only have a H and an R, and even the H is in terms of R. So that means at the end, everything is going to be in this big R. Okay. Okay, it starts from rest. Okay, we like these words. That means initial is 0, 0. Okay, so we get rid of 2 terms. Now these two heights, we want to find the linear speed of the ball when it reaches point P. P is here. What is the height of P? If we call the ground 0, that's just going to be radius, right? Okay, so that means the H final is going to be big R. Now what is H initial? Well, that's the 3.5 R in the problem, right? Okay, so everything is in big R. Now then you need to look up this I for a ball, right? So for a ball, let's go back to the previous slide. For a ball, it's okay. So the I should plug in 2/5 m R squared. Okay, this R is the radius of the ball. Has nothing to do with the big R in this problem, right? What is this big R in this problem? The big R in this problem is the R of the loop. Has nothing to do with the ball, right? So let's just use a small R here. Then we don't have this small r from the problem. So how do we solve this equation? Well, again, don't rush. Don't try to draw any conclusion before you finish the math. Okay, you do the math. So most likely this little r is going to be canceled because the problem even doesn't even tell you the little r. Okay, so a lot of people, they will freak out. They'll be, wow, what do? I don't know this. I don't know that. Do the math. Do the algebra carefully. Okay, things are going to cancel out. It will lead you to the right answer. Okay, now let's do that. So now I'm going to plug it in. 1/2 this times omega final squared, right? 1/2 I omega squared plus 1/2 m v final squared. Okay, this is 0. mg final height is gonna be big R. Initial height 3.5 R. Now solve this problem. Again, you would say, I have 2 unknowns here, omega and v, but they are always connected, right? You can always replace one with the other. If you want to find omega f, you replace this guy with omega f. And then if you want to find Vf, you replace this guy with a function Vf. Because we know that they're always connected by this. Now little r, right? Because this is the radius of the ball. Has nothing with the big R given the problem. Okay. Now I still want to find Vf, right? If the problem tells me to find the omega f, I will write that guy in terms of omega f. So omega f is going to be Vf over R. So omega f squared is going to be Vf squared over R squared. And then you can see that when you multiply this R squared with this omega squared, you will get V squared, right? Because R squared times omega f squared, Vf squared. So you see that at the end, you don't need the radius of the ball, okay? You don't need that, okay? So now let's finish the algebra. So these two guys, you multiply them together, you get V squared. So you will just get 1/2 times 2/5. So you will get 1/5 m Vf squared, right? Because now I just put this R squared and omega squared together, it becomes V squared. M is still there, multiply these two numbers. Now this becomes 1/2, this is still 1/2 Vf squared. And then these two terms, you can even combine them, or move them to the right if you like. Then you will get mg 3.5 R minus R. Right, factor it out. Okay. Then you see that even little m, you don't need that, right? So that's why the problem doesn't even tell you the little m. Okay. So at the end, what do you get? you combine these two terms, so cancel little m on each side. You will get 1/5 plus 1/2 Vf squared equals G 2.5 R. And then, well, you don't even need to calculate. This is going to become 7/10 Vf squared equals G 2.5 R. Right? And then you rearrange this equation. You will get Vf equals 25 R, 25 G R over 7 square root. Okay? So that's going to be B, right? You see, at the end, you only need this big R. You don't need anything else. You don't need the mass of the ball. You don't need the radius of the ball. Okay? So that's what I usually say. Do the math. The math is going to guide you to the right answer. Okay? All right. So this is this question. Now let's take a look at the slide 9. So sometimes you're going to see this type of question, which has a system, and the system has many objects, including rotating or rolling object. So in this case, we have seen this problem in energy part, right? Oh, when two things they're connected by a string, they're moving up and down, I would consider them as system. Apply conservation energy on the system, right? And then you will get many terms, okay? And then again, we usually get many zeros, right? Sometimes it starts from rest or like hits the floor or something like that, or we can just assume the initial or final height to be 0, right? So the only difference here is this. When you see a pulley in this part, you're not going to ignore the pulley, right? When we studied working energy, we never worry about the pulley. But now we're going to consider the pulley because the pulley is rotating. The pulley also has kinetic energy. That's the only difference. That's the only difference, right? So you will just include the pulley in your system. All right? So let's do that. All right, so it's still going to be this, right? But now I'm going to write changing kinetic energy and changing potential energy for every single thing, right? So I have M1, M2, and the pulley, okay? So let's first write down the changing kinetic energy for these guys. So I will get a lot of terms, right? So for M1, I will have 1/2 M1 V1F squared minus 1/2 M1 V19 squared. And the M1 and M2, they're not rotating, right? They will only have this. They don't have any 1/2 I omega squared. So M2, I'm going to do the same thing. Now the pulley, okay, is the pulley rotating or rolling? Rotating. Rotating is going to only have this term. It doesn't have that term. If there's a rolling object in this system, then it has two, right? There's two different versions of kinetic energy. So for the pulley, I will only have this. All right. Now I've done with the kinetic energy. Now let's do the gravitational potential energy. Gravitational potential energy, okay, the pulley doesn't have any gravitational, well, it has potential energy, but it's not changing. So you don't calculate this guy for the pulley. You still calculate delta UG for M1 and M2. So let's do this. Okay, so this is the complete equation, equals external work. This is going to be equal to external work. Okay, so the left-hand side, let's see, you will get many zeros, right? You will get many zeros. For example, the system is released from rest. Okay, nice. 0, 0, 0. Okay, so you see that we already got rid of 3 terms. Now this height, okay, so it says that find the angular speed of the pulley. So we want to find this guy, right? So this is what we want to find, omega f. Okay, then you would say, then V1F and V2F, they are also unknowns, right? First of all, V1F and V2F, they're going to be the same, right? They're moving in different directions, but the value is going to be the same because they're connected by the string, right? So first of all, V1F is going to be equal to V2F. Now I can call it VF, but you can still, you may still say, well, then what about VF, right? So I still have 2 unknowns here. But remember, everything's connected, right? The pulley is moving, the string is also rotating with the pulley. So the string has this velocity, also has this VF, okay? And the string has this VF, and the string is rotating with the pulley, so the VF is again connected to the omega F, the angular speed of the pulley, by the radius of the pulley, right? So this is still going to be equal to R omega F. Okay, so that means all these 3 terms, there's only one unknown, omega F. Okay, so we're good with this guy. We don't need to worry about that. Now, what about these 4 heights? Now let's take a look at that problem carefully. We want to find angular speed of the pulley, which is omega F. We leave it there. After M2 falls down a distance 8 centimeters. So M2 falls down. Okay, M2 falls down, that means M1 goes up 0.8 centimeters, right? Okay, so for M2, I'm going to call the final 0, because final is lower than, this is F, H2F, H2I. So that means H2F, I'm going to call it 0. H2I, I'm going to call it 8 centimeters. Okay. What about M1? So M1, this is H1I, this is H1F, right? So I would just call H1I 0, because H1I is lower than that. So H1I is going to be 0. H1F is going to be 8 centimeters. Now you see that I get rid of another 2 terms, right? So because I'm calling H2F 0 and H1I 0, okay? So now let's write all these terms we are left with. So I can combine these 2 terms, so that's going to give me this. VF squared, right? Plus 1/2 I omega F squared. And then H1 final and then H2 I already know that, so I'm going to write them down. M1G H1 final minus M2G H2 initial equals the external work. Now, what about the external work? Okay, we have done this problem before, right? So how many forces on M2? So let's take a look at our M2. If I want to draw the forces on M2, I would draw gravity and then tension. But gravity never goes to the right-hand side. Tension is inside my system, doesn't do work, right? And you will draw the same Freeburg diagram for M1, right? Gravity doesn't do work. Tension is inside the system. So there's nothing from the outside. These 3 guys in the system, they just interacting with each other. They don't get any work from the outside, right? 0. Now you're going to look up the I for the pulley, right? Because that's the only thing you need. And then let's go back to slide 7. The I for the pulley, so you can model it as the disk, right? So the I, I'm going to plug in. For the pulley, it's going to be 1, is it 1/2? Yeah, 1/2 M squared, okay? Or let's use big R. The problem, I think the problem gives us big R. Yes, okay. So now let's see, let's put everything in. First of all, I'm going to replace this with r omega squared. So I get rid of Vf. So I'm going to have 1/2 m1 plus m2 r omega squared. Right? And this is just going to become r squared plus, times omega squared. And this term becomes 1/2 times 1/2 m. So that's a Pauli, right? So I'm going to use a subgroup. Pauli big R squared omega f squared, right? And then I can move these two terms to the right. So I get m2ghi becomes positive minus m1gh1 final. But these two heights are the same, right? Okay, so I guess I'm ready to solve this equation because omega is only one unknown, right? We know the R, we know the mass, all the masses, we know these heights, okay? So at the end, you will solve this problem. So I'm going to erase this. Okay, so let's first combine these terms, okay? Because only omega is unknown, so you will get this times r squared, right? Each term has r squared, and then 1/2 m1 plus m2 plus 1/4 m Pauli, right? And then because these two heights are the same, so I'm just going to call them h, okay? So you will get m2 minus m1 gh. Right? And then you just divide both sides by everything and then take a square root. Right? m2 minus m1 gh divided by r squared times 1/2 m1 plus m2 plus 1/4 m Pauli and then square root. Right? Okay? And then now you're ready to plug all the numbers in, right? We already have all the numbers. So if you plug all the numbers in very carefully, okay, you will get this answer. Okay? So this is the answer. Okay, so this is another problem for conservation energy, but we do have a linear kinetic energy and rotational kinetic energy. The only difference when you have a system is that if there's a rotating object or rolling object, you're going to write down the kinetic energy for that object, and then that's it, right? The rest is the same as what we did in the energy part. Okay, now we have finished this question. Now we're gonna move on to the next slide. (17). So we have been discussing all these energy, kinetic energy, right? Rotational kinetic. We did a lot of practice. But what did we learn? Recall that in linear motion, after we studied working energy, what did we learn? Momentum and impulse, right? So what is the equivalent to momentum in rotation? There is a quantity equivalent to momentum, okay? See that it's a complete and consistent theory. And this is the last thing we want to introduce in this part, okay? So take a look at the table, the first slide, lecture 17, right? The only thing we are missing on this table is the momentum in angular motion, so we're going to call it angular momentum. And then what is the equation for angular momentum? Okay, take a look at the slide 2. So angular momentum is also a vector, okay? Because momentum is a vector, right? You see, it's a consistent, complete theory. It's so beautiful, this theory. Okay. Then what is the definition of angular momentum? The formal definition of angular momentum is this, okay? So we use the symbol big L to denote angular momentum, big L. So this is a vector. So the formal definition of angular momentum is this. It's a cross product between this r vector and the linear momentum of the object. So linear momentum is p, right? We already know that it's just mass times velocity. The r, so take a look at the image on slide 2. Anything moving, so you can pick, if something's moving, right, you can pick a little piece on this rotating object, which is a particle. Then you can draw a line from the rotational axis or pivot to where this particle is, right? So that's an r vector, you can see that. And then r is a vector, p is a vector. You can make a cross product out of these two guys, right? And then you will get angular. This is the formal definition, okay? This is a definition. This is the best definition physicists have found, okay? And then because p equals m times v, this is also equal to this. I'm just using the definition of a linear momentum. So then, if you want to use this equation, find angular momentum, you would do it in 2 steps. The magnitude is going to be this, right? And the direction is going to be right-hand rule. So if you have r and p on the image, so the angular momentum is going to be straight up. Again, it's very non-intuitive, right? The object is rotating this way, but the angular momentum is straight up. But again, that's the only way to make a consistent and complete theory in physics, okay, in angular momentum. But we don't need to worry about this vector equation, okay? So because we're just going to be working on the same plane, okay? So, but there's also a law called conservation of angular momentum, because that's the third conservation law we learned in this class. Conservation of energy, conservation of momentum, now conservation of angular momentum. So what is the conservation of angular momentum? Okay, it's this. Changing the angular momentum of system equals this thing. So you're going to integrate the torque, which is also vector. Now we're going to use all the vectors, or you integrate the torque over time. And then every external torque, you're going to do this integral, and then you will add all these numbers together. Does this look familiar? Yes. What is changing momentum in linear motion? What is conservation of momentum? Changing the momentum in linear motion equals external impulses added together. Then you would say, well, the right-hand side doesn't look the same. What is the definition of impulse for any force? This is defined as the integral of force over time. Now compare these two laws. Exactly the same. All you need to do, replace momentum with angular momentum. Replace force with its equivalent in rotation, which is just torque. Okay? Isn't that beautiful? Okay? So we call this guy impulse, right? We have a new name for it. We have a new symbol for it. So you could also call, if you like, you could call this thing, this integral, angular impulse. But physicists just didn't do that. Okay? But again, this whole thing is just equivalent to the impulse we define in linear motion. Okay, all right. So this is conservation of angular momentum. But in this class, we're not going to be really working with this vector equations, because that's too complicated for this class. Okay, so all we need to do is to work with the a simplified equation, which is on slide 3. Okay. So slide 3 is this, okay? You can then, this is for every little piece on this rotating object, right? You do this, and then at the end, you will add all these little pieces together, Okay? So at the end, if you add all these little pieces together, the angular momentum at the end for a rotating object is just going to be this. You add all these things together, you get a sum Ri squared, and then times omega. You need to do the math to get this, right? So we don't want to do that here. And then it's always straight up, so we call it z direction. So you will see this subscript there. But what is this guy? Again, we define this guy to be I, right? So we're going to call this I omega. So this equation is going to be the equation we're going to use in this class. This is a simplified equation. We're going to forget about the vector equation, even though that's the formal definition. And then compare this with the linear momentum. I is moment of inertia is equivalent to mass. Angular velocity equivalent to velocity. Perfect. Everything is consistent, right? Okay? So when we apply this law, conservation of angular momentum, the left-hand side, we're just going to do this. I times omega, like m times v. Calculate this final value, initial value, subtract them, right? So that's how you find the change in momentum. The right-hand side, okay, well, then you still need to do this. Then a lot of people are scared by this integral. But we're not going to really integrate anything. So in this part, the torque and force, they're still going to be constant, right? If this number is a constant, you integrate over time, you just get the torque times time, right? So the right-hand side is going to be this, okay? And the left-hand side is going to be this symbol, okay? So that's how we use conservation of momentum in this class, okay? Use that to calculate the left-hand side. It's like m and times v, and then for each term. For the right-hand side, if there is some torque, you would just do torque times time. It's like the impulse, right? If the force is constant, you do force times time. And then add all these contributions, put it on the right-hand side. That's conservation of angular momentum. Okay? So I'm going to stop here.